Now, packet tracer, the lab building a switched network with redundant links, uh, PDF lab. In this video, we're going to be building a redundant link using three switches, switch S1, S2, and S3. Just drag three switches. We took three 2960 series switches, two, three, and we name it switch 1. This is switch 3, and this is switch 2. Now, according to the topology, we use the cables, crossover cables, because this is a like devices, so we have to use the crossover cables. When it's like devices, the crossover cables are used, and when it's unlike devices, straight through cables are used, except few exceptions. Such as router to end device, such as computers or server. In that cases, we use also crossover cable. So switch 1 fast Ethernet goes to the switch 2's fast Ethernet, and then switch 1's fast Ethernet 2 goes to the switch 2's fast Ethernet 2. Now switch 1's fast Ethernet 3 goes to the switch 3's fast Ethernet 3. And switch 1's fast Ethernet 4 goes to the switch 3's fast Ethernet 4. Now these two, switch S2 and S3 fast Ethernet 3 goes to the fast Ethernet 1 of switch 3, and fast Ethernet 4 goes to the fast Ethernet 2 of the switch 3. And now, what is redundancy? Redundancy is a use of multiple switches or multiple links between switches. Even though redundancy increases availability of the device and prevent failure, it can cause loops and duplication of frames because there are many logical paths. So spanning tree protocol ensures one logical path between all destination by blocking redundant path that can cause loop. Now let's configure those switches. We're not going to do this. We only are going to be showing how to configure from this section, and then copy running config and copy and run, copy running config, start config. This is what we're going to be doing. First, let's go to the address tabling. We see here that you have a switch 1 VLAN 1, switch 2 VLAN 2 have they all have IP address and subnet mask. Now why VLAN 1? Now VLAN 1 is also a native VLAN. By default, any traffic that is untagged, means not coming to any of the VLAN, goes to the native VLAN. A native VLAN by default assigned to trunk ports. Trunk ports are links between switches that uh, s- that support the transmissions of traffic coming from many VLANs, as well as the traffic that does not come from a VLAN, such as like untagged traffic. Untracked traffic doesn't come for any VLAN. This VLAN one is also by default a management VLAN. So when we assign an IP address to a management VLAN, such as VLAN 1 by default here, they need we can access it remotely. We can manage it via HTTP, Telnet, SSH, or SNMP. Now, to create management VLAN, the switched virtual interface of that VLAN, not the real interface, the virtual interface of that VLAN is assigned an IP address and subnet mask. Now also, by default, all ports of all switches are assigned to VLAN 1, and this allow any device to communicate to any switch port if it is connected. If it is connected, this means that switch S1, S2, and S3, they can now communicate if we make the connections, if we connect the cables. And now let's configure the IP address for VLAN 1, for VLAN 1 of the switch 1. We go to the command line and we do enable config t, and now we type interface VLAN 1, and now IP address. What is the IP address of the VLAN 1? IP address 192.168.1.1. You can see it IP address here. 192.168. 192.168.1.1, 255.255.255.0 subnet mask. What did I make wrong? 192.168.1.1. Oh, I didn't put the address. IP address 192.168.1.1, 255.255.255.0, and then we put no shut. Now interface is up. Now let's go to the switch 2. Go to the command line interface. We enable config t interface VLAN 1 IP address. What is the IP address of VLAN 1? VLAN 2, switch 2. 192.168.1.2. 192.168.1.2. And then subnet mask 255.255.255.0, and with no shutdown. Now interface is off. And now we go switch 3. We go to the command line, enable config t interface VLAN 1, and what is the IP address? 192.168.1.3. 192.168.1.3. Oh, we didn't put the IP address. One nine two dot 168.1.3 255.255.255.0 and then no shut. Now all the interfaces is up. This VLAN interfaces is up. Now we forgot to copy it to our configurations. We go to the privilege executive mode. We type copy running config start config, or we can type WR, which is that will also copy it the running config to startup config. Forget to NWR. We go privilege mode, executive mode, and type WR, and everything has been saved. And the startup config. Now test the connectivity. Now we know that this VLAN's VLAN 1 is all this switch has a VLAN 1 by default. All the ports are assigned to VLAN 1 for the switch 1, and for the switch 2 by default all the ports are assigned to VLAN 1, and for the switch 3 by default all the ports are assigned to VLAN 1. So, and then we have configured an IP address of the VLAN 1. All these IPs, so theoretically switch 1 was supposed to be able to connect to switch 2, switch 2 connect to ping switch 3, switch 3 was supposed to ping switch 1. So they both are now should be able to ping each other's. So now let's test the connectivity. So we are in a switch 1. We type ping, ping switch to 192.168.1.2. 192.168.1.2. You see, success rate is 60%. Now success rate 100%. And now if we try to ping switch 3, which is 192.168.1.3. So PC1 can communicate with PC2 and PC3, and PC2. So now we have shown that they are connected to each other's. Each switch is connected to each other's. Now determining the root bridge. Now every spanning tree instance, has a switch designated as a root bridge. Root bridge serves as a reference point for all spanning tree calculation to determine which redundant paths to block. Let's discuss a little bit about root bridge, because it's very important. Without understanding the root bridge, there's redundancy. It's very hard to understand how redundancy works in a switched network. Network in a redundant network, a single point of failure may be a switch failure or a cable failure here. Usually a network distribution layer, you need multiple switches so that you can minimize chances of failure. But when you introduce multiple switches in a network, there are drawbacks. Two, there may be loops and duplicate frames, which has very severe consequences to the network. So, to prevent this loop and duplicate frame, spanning tree protocol has been developed. Spanning tree protocol runs on spanning tree algorithm. This spanning tree algorithm designates a single switch as the root bridge and use this switch as a reference point to calculate the best path while blocking the other path. You can see in this animation video to comprehend how STP choose to block the path. In this video, you'll see that the PC1 sends the broadcast out onto the network. Switch 2 is configured with STP and has set the port for trunk to a blocking state. The blocking state prevents ports from being used to forward user data, and this prevents loop. Switch to forward a broadcast frame out all switch port except the originating port from PC1 and the port for trunk 2. Switch 1 receives the broadcast frame and forward it. Switch 1 receives the broadcast frame and forward it out all of its switch port where it reaches PC4, and switch 3. Switch 3 forward the frame all of its port phase to terminal 0/2 because it cannot forward phase to terminal 0/1. This is the originating port because switch forward all the frames except the port it has received. And when the switch 2 receives this frame, it drops because this trunk has been blocked. This is the blocking port, and this is how the switch 2 prevents the loop from forming. Now let's take a look at the video. PC1 is sending a frame to switch 2, and switch 2 forwards the broadcast out all port except originating port and the block port. Now S1 forward the broadcast out all port except the originating port, and S3 receives the frame and forward it now in this pictures you're going to be seeing STP recalculating when a failure occurs. The trunk link, which is S1, the trunk link between S1 and S2 has failed. This has failed. S2 unblocked the ports. You will see that the S2 unblocked the ports for trunk 2, and then PC1 sends a broadcast frame to S2. S2 forward out all of the port except the originating port. It forward here and forward here, but it only do not forward this port, and failed link for the trunk. Sorry, the PC1 is not going to be forwarding this one because this is a failed link. Now S3, once it received, forward broadcast out all available port except the originating ports. It receives here and it is going to be forwarded out this way because it cannot forward out this way. This is the originating port. And now S-word forward broadcast only out fast Ethernet 03. It cannot block this way because it cannot forward it this way because this is a blocked port. Now let's play the video. Now, how STP select a root bridge and block other ports? Root bridge is selected through a participation process. All switches that are participating in STP exchange BPDU frames to determine which switch has the lowest bridge ID or BID on the network. The switch with the lowest BID automatically becomes the root bridge for the STP calculation. Now let's discuss little details about BID and BPDU. Now, spanning tree algorithm depends on exchange of BPDU to determine a root bridge. A BPDU frame contains 12 distinct fields that convey the path and priority information used to determine the root bridge and the path to the root bridge. There is a 12 field here. The first 4 fields identify the protocol versions, message type, and status flag. The next four fields are used to identify the root bridge and the cost of the path to the root bridge. And the last 4 fields are all timer fields that determines how frequently BPDU messages are sent and how long the information received through the BPDU process how long the information received through the BPDU process is retained. As the switch forward their BPDU frame, adjacent switches in the broadcast domain read the root ID information from the BPDU frame. If the root ID from a BPDU received is lower than the root ID on the receiving switches, then the receiving switch updates its root ID, identifying the adjacent switch as the root bridge. Now, in the first picture shows spanning two instances, where a switch designated as a root bridge. The root bridge serves as a reference point for all spanning tree calculation to determine which redundant paths to block. An election process determines which becomes the root bridge. Now, in the second pictures, it shows that the BID field. The BID field is made up of a priority value and an extended system ID and a MAC address of the switch. Now, BPDU frame lowest BID ends up being identified as a root bridge. So, if a priority value is the lowest in a BPDU frame, that identifies being as a root bridge. The lowest priority value that root bridge is for that spanning tree instance only. The lowest priority is the lowest BID, which with the lowest priority value becomes the root bridge. The lowest priority actually takes the precedence. So if you want a switch to become root bridge, set the priority value as the lowest. The bridge priority is range from 0 to 61,440, and it is incremented from 0 by 4096, such as 0, 4096, 8192, and so on. A bridge priority of 0 takes the precedence over all other bridge priority. Now the extended system ID. A BID has a 2 byte of 16-bit value field, 4 bits for the bridge priority and 12 bits for extended system ID. This 12-bit identify the VLAN participating in this STP instance. You can see rightmost 12-bit for VLAN ID and leftmost 4 bits for bridge priority. This explains why bridge priority value is configured 4096 increment, because 2 to the power 12 is 4096. So the VLAN in the BPD frame is the 12-bit value in the state extended ID, the extended system ID. The 4-bit bridge priority value and 12-bit extended system ID is called BID. When two switches are configured with same priority and same extended system ID, now switch with the lower MAC address then will be determine the lower bridge ID, and the switch with the lower MAC address in this instance become the root bridge. Now in this picture, in the second picture, we see that S1 has a lower priority than the other switches. S1 is a 24577, and this one is a 32769. This one is 32769. So S1 has the lower bridge priority, and therefore it becomes the root bridge. The spanning tree like this one is a root bridge. And in this picture, you see that when all switches are configured with the same priority value, this one has the 32769, this has a 32769, 32769, and a default priority value configuration is 32768. Since every switch is a one path away, this is one is added to 32768 and becomes 32769. So all three switches has a default priority value of 32769. So the MAC address will become the deciding factors. So MAC address for switch 2 is the lowest one. It has a 111 value as the last digit. This is 333222. So this is the lowest MAC address, and this become the root bridge. Now, after the root bridge has been determined, the STA, which is spanning tree algorithm, calculates the shortest path to the root bridge. Each switch uses spanning tree algorithm to determine which port to block, while spanning tree algorithm determines the best path to root bridge for all switch ports in the broadcast domain. Traffic is prevented from being forwarded to the network. The spanning tree algorithm considers both path and port cost when determining which ports to block. The path costs are calculated using port cost value associated with port speeds for each switch port along a given path. The sum of the port cost value determines the overall path cost to the root bridge. If there is a more than one path to choose from STA, from a spanning tree algorithm, choose a path with the lowest path cost. Now in this picture you see the default port cost. The default port costs are defined by the speed at which the port operates. You see the 10 gigabyte Ethernet port have a port cost of 2. 1 gigabyte Ethernet port have port cost of 4, and 100 megabits per second Ethernet ports have a port cost of 19, and 10 megabits per second ports have a port cost of 100. So as the speed decreases, the port cost increases. Although switch have a default port associated with them, the port cost is configurable, and an administrator can configure the port cost and control spanning tree paths to the root bridge. Now to configure the port cost of an interface, and you simply use spanning tree cost command in the global configuration mode, and in the interface configuration mode, and then you type what is the port cost that you want to set. In this instance, we set the port cost 25, but port cost could be we can use from 1 to 200 millions to set the 1 to 200 million and this is the range that we can select as a port cost. In this example, switch port fast Ethernet 0/1 has been configured with a port cost of 25 using the spanning tree cost command, and it is on the fast Ethernet 0 interface. Now if you want to restore the default value, which is 19, you simply need to enter no spanning tree cost. This will restore the default value of port cost 19. Now in this example, the path cost from switch 2 to root bridge to root bridge S1 over path 1 is 19, which is the default value. While the path cost over path 2, this is the path 2, is 38, because this is going to be 19 and another 19. So this is 38 because path 1 has a lower overall path cost to the root bridge. It is and preferred. A spanning tree protocol configures path 2, which is redundant path, to be blocked, and this is how STB prevents a loop. So the path cost is equal to sum of all port cost along the path to the root bridge. Path with the lowest cost become preferred, and all other redundant paths are blocked. Now to verify the port and path cost to the root bridge, enter the show spanning tree command. The cost field near the top of the output is a total path cost to the root bridge. This value changes depending on how many switch ports must have traversed to the root bridge. In the output, each interface is also identified with an individual port cost of 19. Network now determine determine the root bridge. So first we're going to be deactivate all ports on the switch. I know we have a 24 fast Ethernet port and 2 gigabit Ethernet ports. So we deactivate all of them. It is a best security practice, safe practice, once we deactivate all the ports and we activate only the ports that we need. So we go to the switch 1. We are in the global configuration mode. We type interface fast Ethernet 0/1 to 24. So this 24 fast Ethernet port and 2 gigabit Ethernet port 0/1 to 2. Oh, we didn't put the range. Interface range fast Ethernet 0/1 to 24, and then gigabit 0/1 to 2. And now we shut down. And now we do the same things for switch 2. We're in the global configuration mode, so type interface range fast Ethernet 0/1 to 2, then gigabit Ethernet 0/1. No, fast Ethernet 0/1 to 24, because there are 24 fast Ethernet port, and gigabit 0/1 to 2 gigabit port, and then we put shutdown. And now we go switch 3 and we do the same things. We're in the global configuration mode. Type interface range fast Ethernet 0/1 to 24, and then gigabit 0/1 to 2, and we put shutdown. Now all the ports has been shut down in this switched networks, and now activate port, configure the connected port as a trunk port. Now obviously we need to configure it as a trunk port, otherwise no VLAN transmissions is going to be occurring, no VLAN tag transmission is going to be occurring, because the ports, in order for the ports to carry the VLAN tag, there has to be the trunk port. The other one is the access port that only are connected to the end device. But when it's a switch to switch, switch to switch, and switch to switch, and they are going to be carrying VLAN tag for all the devices, there has to be a trunk port. Now, how many ports we have? We have here fast Ethernet 404, fast Ethernet 3, fast Ethernet 2, and then fast Ethernet 1. So 1, 2, 3, 4. This 4 port is going to be trunk. So we go global config mode, interface range fast Ethernet 0/1 to 4, and we type. Now if we hit a question marks, we're going to see what are the available options that we have. We can see that we need this one, switch port mode, switch port. So if we hit the switch SW, and if we hit the tab button, that'll tab complete and type it for you, switch port, and then mode trunk. And then once we do the switch port mode trunk, for the switch S1, we're going to be activating port only fast Ethernet 02 and fast Ethernet 04 of all ports. So this is what they want us, the instruction. activate Fast Ethernet 2. This is 4, this is 3, this is 2, and so it's a 2 and 4. These two links we're going to be activating. This one and this one. So interface range Fast Ethernet, /2, and then Fast Ethernet 0/4, and we put no shut. So this two interfaces up. Now we do the same things for switch 2. We first configure all the connected port as a trunk port. Exit to go global config mode. Interface range. There are four ports. One Fast Ethernet 1 to Fast Ethernet 4. FA 0/1 to 4. Switch port mode trunk. Switch port mode trunk, and then we activate Fast Ethernet 2 and Fast Ethernet 4. Interface range Fast Ethernet 0/2 and Fast Ethernet 0/4, and we put no shut. And now we do the same things on switch 3. Exit to go global configuration mode with the interface range Fast Ethernet 0/1 to 4. Switch port tab completion mode trunk, and then we activate Fast Ethernet 0, 2 and 0/4. Fast Ethernet 0, 2 and 0/4. Interface range Fast Ethernet 0/2, Fast Ethernet 0/4, and then no shut. Now display spanning tree informations by using show spanning tree command. So we go switch S1 and type and we go to the privilege executive mode and type let's see, we do a question mark, or we can use show command, and so we should show, and then we hit a question mark. We can see spanning tree. So show spanning tree. We hit SPA and then hit tab completion. We see that we can the CLI has typed it for you, spanning tree, and we hit enter, and we see that this bridge is the root bridge. This is the root bridge. The bridge priority here is 32,769, MAC address is 59 bridge priority and then it has a local priority 3269. This is the root bridge. The priority is 32769. So this is how and it has a MAC address of 59 DC. So you can see all this information, priority, MAC address, and it can also show you that most of the port FAST3002 and FAST30 port is a designated port, and it's on forward state, and it has a port cost of 19. Now we go to the switch 2. We go to the Triple H executive mode, and then we type show spanning trap completions, and it also shows the span entry information for this switch. It has a address which is 59 DC, and it has a priority of 32769. It has a one port that's a root port, and then it has a one port that's in block port, and the cost for each port is cost for each port is 19. Now we see we make a comparison between switch 1 and switch 2. Why S1 is the root bridge and S2 is not? They have both priority is 32769, and their bridge ID priority is 32769, and address is this one 00E0. This figure and this address is 0002. So this 0002 in a hexadecimal is much lower than 0004. So they have the lowest MAC address. They're the same priority, but the different MAC address. So this is why S1 has chose to become the root bridge. Now, how S1 learned that its MAC address is lower? It learned by port FAST2, FAST2 0/2. This is the port S1 has learned by. You see the S1. S1 has learned via this port, FAST3002. These are the one that's activated port. Other ports are not activated. So S1 has learned that it's a root bridge. Its MAC address is lower than switch 2 via this port. Now we use the show span entry command on switch 3 to examine in why why S1 become root bridge, not S3. So go enable, we go show span entry. Now we see that in a switch 3 bridge ID, priority, and this priority values are same. So what is the difference? The MAC address is 00D0 and 0002. So 00D0 is much higher than 0002. So this is how switch 1 figured out that its MAC address is lower, and therefore it is the root bridge. S1 is learned by port 4. So that this is the information fast Ethernet 04 that has given so S3 has given information to the S1 via port 4. See, where is the port 4? So S1, and this is where the port 4 is. So you can see the port 4 is activated, and port 4 is the one that has given information to the S1 that their MAC address is lower. Switch 3's MAC address is higher than switch 1, and therefore switch 1 has become the root bridge. Now, based on the output from your switches, answer the following questions: which switch is the root bridge? So, so switch S1 has become the root bridge. We have figured it out before. S1 is the root bridge. It shows the information here. This is the root bridge. And which ports are designated portions on switches? So if S1 is the root bridge, fast Ethernet. If S1 is the root bridge, fast Ethernet 04 and fast Ethernet 02 is the designated port, but it's also the root port, because the switch with the root port, all their ports are the switch with the root bridge, all their ports are root port also. That will, when we next section we go to the port role, we'll figure that out. And which ports are designated ports on switches? Which ports is showing which is the designated port of the switches? The designated ports, fast Ethernet 04. Let's go to the switch 1. The designated port is the fast Ethernet 04 and fast Ethernet 02. And let's go to switch 2. The designated port, there is no designated port on switch 2. One is a block port, that's a fast Ethernet 04, and fast Ethernet 02 is the root port, because fast Ethernet 02 is closest to the root port. Fast Ethernet 02 of the switch 2. This is the switch 2. So 02, and this port is the closest to the root bridge, and this is why fast Ethernet 02 is the root port. And then we go switch 3. We see that the fast Ethernet 02 is the designated port, and 04 is the root port. 02 designated and 04 root port. Here is the switch 3. This is the root port because it is closest to the root bridge, and the designated port is fast Ethernet 02. This is the designated port. Now, what port is showing as an alternate port and is currently blocked? Okay, let's go to the switch 1. Switch 1 does not have any alternate port. These are all designated port. And let's go to switch 2. Enable show spanning tree. Switch 2 does not have any alternate port or block port either. So, and then go to the switch 3. On the switch 3, switch 2 has an alternate port or block port, which is fast Ethernet 04. Fast Ethernet 04 or switch 3 is the alternate port. Fast Ethernet 04 of the switch 2 is alternate port. So this is the one that has been blocked. You can see here that it is neither on nor off. It is, if it's on, that means this is a green light, and if it is off, that means it's a red light. But this is neither red nor green, it's orange, and this is why it indicates it's a block port. Now, which ports are the switches? Okay. Why did spanning tree select this port as a non-designated port? So why did spanning tree select this port as the non-designated port or block port? Because the spanning tree algorithm uses root bridge as the reference point, and then determine which port to block based on path cost. If the path costs are equal, then compares the BID or bridge ID. Lowest number are preferred. The link between switch 2 and switch 3 has a higher cost to the root bridge. Link between switch 2 and switch 3, it has the highest cost to the root bridge. So to reach the root bridge, this, if they follow this path, so you have to one path and if another path, so two paths. So this is going to be costing more, because each path has their own default value, as we have discussed earlier in the root bridge selection process. So this way is going to be more expensive, and this is why they have blocked this port, and they keep this port open, because it is the fastest route to get there. The cost is much lower. So, so if the switch 3 to get to the root bridge, it has this path, and switch 2 to get to the root bridge, it has this path, this one, and this one at the same cost. But to get from switch 2 to switch 3, he has to go switch 3. This is one path and this is another path. So this is the redundant path, and this is why redundance means like more than they need. Extra. Redundant means extra. That's why they have blocked this extra path and extra cost.